Ising model. Okay. 2 weeks? We'll finish it anyway. Alright, so what we are doing, and this is the last part of this class, so basically Ising model and Ginzburg-Landau theory immediately afterwards. So hold tight, we're almost there. If you remember all the things that we managed to do this semester in statistical physics, and this is the mantra that I was repeating once and again and again and again from the starting point of this class, is that eventually we are trying to treat everything as if all the particles or the degrees of freedom or effective degree of freedom of or particles are independent. Right. This is what I was trying to tell you all along. Now the problem is that in most cases it is true, but there are some cases where interactions, or there are something that we just call strong interactions. And those strong interactions cannot be made simple or not strong interactions. They are sometimes not negligible, and they cause the system to behave in a very different fashion from what a system of independent particles would behave. Now, this is what happens for magnetic systems, right? So we are going to try and see how those strong interactions can cause phase transitions, right? Now, in most cases, in real life, usually we don't have strong interactions. In a lot of cases, we simply can say, well, I have some interaction, there is an interaction length, and I can neglect this as we have done so far. But when we're treating phase transitions, specifically second order phase transitions or continuous phase transitions, then those strong interactions are not negligible. They cause the system to behave in a completely different fashion from what we expect. What is for me a magnetic system? So let's assume that I have a material. Inside this material there is a lot of atoms or electrons, whatever. Now, some of the electrons that are spread around the system, especially electrons in the unfilled levels, they have spins. Now, usually because of the random orientation of the different atoms, etc., the orientation of those spins is completely random in space. Okay. So those vectors are some vectors of the spins that we have inside the system. Now, when I'm thinking about spin, I can also say, well, there is a magnetic or self-magnetism that I will call mu. And this is the magnetic momentum of the material, okay, which is basically a sum of the effects that are coming from all the different electrons or all the different atoms that we have inside the system. So we have a magnetic moment mu. Okay. If we apply an external field, H, right, to the system, so the total energy of the system becomes mu dot H, right, with a sign of minus, okay, with a sign of minus. So what happens if I apply an external field on a magnetic material, or there are some magnetic particles inside this material? All the different spins would like to align exactly the direction of H. How do I see this? How do I see this? Well, because, well, when I apply an external field, the energy is exactly the magnetic moment dot H. So if they are aligned, this is a maximum, and then the energy, because of the minus sign, is going to be minimal. And we know that in thermal equilibrium, the energy has to be minimal. Right? So this is what happens. I apply an external field all those guys starts to align with respect to the external field, and then they can form something which is, if this field is strong enough, magnetic field. H is a magnetic field. So what happens is that all the different atoms or those particles, electrons, their spins are aligned with this field. So what I managed to create is an ordered state. Okay. This stuff usually is disordered. Okay. Why disordered? All the orientations of the different spins that I have inside this material, okay, completely different orientations. So usually the total spin, if I'm looking only on the total spin, is going to be 0, right? But when I apply an external field, okay, you see that all the different spins try to be aligned with respect to this field, and I'm transitioning into an ordered state. So when I'm talking or going to talk about phase transitions, I'm going to describe transitions from a state which is disordered, okay, to a state which is ordered. And we do know that when I apply an external field, that this transition happens. Okay. Now, so this is simple physics. I apply the field. All the different ingredients have to turn around with respect to this field. Everything is ordered. This is simple. But more than 100 years ago, Pierre Curie found out something a little bit different. So what Pierre Curie had found out. So if we plot, so if we have temperature and we have M, which is absolute value of M, which is the total spin of the system. Okay, which is the total spin of the system or the total magnetic moment of the system. Right? So what do we know? We know what we expect. Usually that, well, there are specific magnetic systems, usual magnets, when all the spins are oriented. So they are somehow ordered. Okay? But in most cases, when we look on a system, right, all the different spins are disordered. So we expect that the total magnetic moment M is total magnetic moment. Okay. They are going to behave differently. How they're going to behave? So for large temperatures, the total magnetic spin is exactly 0, right? But when we cool down the system, when we approach a specific temperature, let's call it TC, T Curie, and then suddenly we do not have I have to emphasize this. We don't have an external magnetic field, right? But suddenly the total magnetic moment of the system starts to rise up and behaves in this fashion. Now this is total magnetic of the system. If I would plot not the absolute value, but the regular value, okay, actually it can behave either like this or like this. Right? So I take a specific system, I start from a high temperature, I cool it down, I cool it down, I cool it down, I cool it down, I reach a specific temperature, critical temperature, TC, and as I cool the system a little bit below TC, what can happen? So either my magnetic moment is going to rise up, okay, and then reach a constant value, or it's going to get down below 0 and again reach this constant value. So this is, we can call M0, and this is minus M0.
Can you say again what is the מה זה הקו האדום ומה זה המקווקו?
It's the two possible behaviors of the magnetic moment. Okay? The absolute value is going to be only this red line. Okay, so it's totally symmetric with respect to reflecting it around the x-axis. Right? So this is actually what we call now disordered state. An ordered state. Why call it an ordered state?
Looks pretty all good.
There is order. There have to be order because if it was zero, so every different spin is actually independent of any other spin, so the total spin or magnetic moment of the system is exactly zero. When the total magnetic spin of the system is not exactly zero, so there is a huge group, a big enough group of different spins that are aligned and pointing exactly in the same direction. Okay? So we are going from disorder to order without applying any external field. Right? We do not apply any external field. We just cool down the system. Nothing happens. So I'm just changing the temperature and I'm crossing this abrupt behavior and I'm going either up or either down. So two questions. First of all, the system has to be symmetric. Right? So this symmetry means that there is no preferred direction. The symmetry is everywhere. Right? This direction has the same weight as this direction, or as this direction, or as this direction. This is a symmetry. Here the symmetry is broken. Why it's broken? There is a specific axis, one single axis that dictates everything. Okay? So this symmetry that I don't care where to point out, and now suddenly I do care where to point out, it's called a symmetry breaking. And what happens over here is called a spontaneous symmetry breaking. Now, this spontaneous symmetry breaking I can understand when I applied it again, an external field, because there is a preference due to external conditions. But here there are no external conditions. The conditions are exactly the same. Right? I have the same system, I have the same atoms, I have the same interactions between the different atoms. Okay? And suddenly, hop, there is a preferred direction, although there are none beforehand. And the symmetry that I have over here is completely gone. Okay?
But it's not suddenly.
It's suddenly.
You called it.
I was here, Tc plus epsilon. No matter how small this epsilon is, it was zero, right? And then I cross this line and it's not zero. So it's continuous. You're right, it's continuous, but it's sudden. And I will explain what I mean by sudden. Okay?
Does
Yes.
it happen to the other way around? If you go from small temperatures to high temperatures, you get
Great question. I will answer it in a second. Great question. Okay. So this is a paramagnetic state. Paramagnetic state. And this is ferromagnetic state. Great. Now I'm coming to this question. So this is one experiment. There is another experiment that describes what happened to those ferromagnets. So, interesting behavior. Low temperature ferromagnets, everything is ordered. High temperatures paramagnetic, everything is disordered. Okay, so this is order-disorder transition. That's what we see over here. Now, in order to describe order-disorder transition, we use something that is called order parameter. So M is order parameter. When it's zero, there is no order. When it's not zero, it's something. Now, all of this we are treating thermodynamic limit, meaning our system is large. Because if we have only two spins, well, there are some fluctuations. Sometimes they are pointing exactly the same direction. Sometimes they are pointing in a different direction. Okay? There is no transition in small systems. But for large systems, this is something very, very peculiar. Okay, so, yes?
Does a large system means a large amount of particles?
Yes.
Does it mean a lot of spin directions?
No, just large amount of particles. Okay. Yes?
כשאתה אומר ferromagnetic state, זה בעצם תמיד ה-order state?
Yeah. Ferromagnetic is the order state. All right. A different type of experiments that occurred exactly at the same time is the following. So we take the same M, and remember that we have this external field H, and we measure, all right, and we measure how M depends on H. Okay, so we first look on what happens when T is larger than Tc. So I start from 0. And I increase H. Right now, all the spins are above Tc. I'm in this disordered state, paramagnet. Okay. I increase H. All the different spins try to align with respect. All the different single magnetic moments try to align with respect to this external field. All right. And as I increase this field, right, more and more spins try to align with it. Why? Because the energetic gain is becoming larger and larger. Okay? Energy is minus mu dot H. Okay, so the larger is H, the smaller is energy, the more preferable those states become. Okay? We know this from statistical physics. The lower the energy, the more preferable the state is, the higher the probability that the spins will align with H. Great.
Can you repeat this again slowly, please?
Slowly. So, the higher the H, the lower the E. The lower the E, the more preferable the state is. That means the more preferable the state is, more spins aligned with H. Okay? So this is how it goes. More spins aligned with H, the larger the magnetic moment. Okay? Effectively, what happens? Yes.
למה קראת להם האורדר פרמטר?
Because I need something to distinguish between why M is an order parameter. This happens here when M is 0, and it's described for me, the situation when all the different spins are uncorrelated and point in different directions. Here, M is not 0, that means that there is a group of particles that are pointing exactly that, a group of spins that are pointing exactly in the same direction. Yep, you will see it in a second. M0 is the maximal magnetic moment that the system can have. Then every spin is aligned with H. Yep. Every free spin. Okay, so what happens over here? We increase H according to what we said. E is getting lower. The states that are aligned with H are more preferable. The states that are aligned with H are more preferable. The larger amount of spins are pointing in H direction. The larger amount of spins that are pointing in H directions, the larger the magnetic moment. Okay? So this is what we have. So we start from 0, we heat up, and then we go somewhere over here. Okay? Now this somewhere over here is this M0 that I see. This is the total, call it M0. This is the total or the maximal magnetic spin or magnetic moment that the system can have. So I'm going in this direction, I'm increasing H, and I'm converging to a specific value. Great. Now, I'm saying let's go in the other direction. I'm here, and I start to lower H, right? So my magnetic moment of the system is what? Is M0. Is M0. It's clear over there? That's M0? Yeah, great. Okay, so I'm starting from here, and then I'm going down because I'm now decreasing H. Okay, so I'm going in this direction. what will happen? Eventually I will reach to 0, and then I will continue downwards towards minus m0.
Yeah.
There is no hysteresis. This is how exactly as I prefer it to behave, right? So there is a loop, there is no loop. I'm going up, it's going to a specific constant value. I'm going down, it's going to the same value, but with the minus sign. Okay? But this only happens above TC. What will happen if I'll do the same trick below TC? So I'm H. Okay. And this is M. Okay. And I'm asking you the following question. Let's assume that I'm somewhere over here. Okay. So this is my value. I applied big field. My magnetic moment is high and it's positive. Now I'm starting to decrease. Right? Now I'm starting to decrease my external field. What will happen? The magnetic moment will start to decrease. Okay? And it eventually will cross 0. When H is 0, it will cross this m-axis at some non-zero value. Why? Well, this non-zero value can be obtained from this plot over here, because this is when H equals 0, no external field. Let's try this. Okay. So when I'm below TC, I'm somewhere over here. I can find from this plot what? I can find a specific value of the magnetization, okay, of the magnetic moment of the system, given that I'm below TC and there is 0 external field. Okay? So this is why this is not 0. Okay. Now I'm going down. And then eventually goes to some minus value. Go with minus m0. Yes?
When do we start from M0 at...
I'll explain you in a second. I will explain you. Don't worry. Let me write this result and then I'll explain you why I started from M0. Oh, so this is the question, right? So now I'm reversing everything. I'm saying I'm starting from minus M0 and I'm going up. What will happen? No. So first of all, the system is not reversible. Right? The system is not reversible. Why? Because I know that if I started from a minus sign and eventually I will reach the 0 external field situation, you can say, well, Stas, you have to go exactly to the same point over here. Right? This is the point. This point. But what happens in reality, and this is why I plotted to you the upper solution and the lower solution, is that there is analogous point, which is minus. It's just a reflection of this M0. We just reflect everything over here. Yeah, I will explain in a second. And then it goes like this. Okay. And this is the hysteresis loop, as you mentioned. Which basically says the following. I'm starting from a specific position, I'm going down, and it's a different behavior than when I reverse everything and I'm going up again. How this behavior over here is related to, well, this is clear, right? This is the usual physics that I will assume. I'm reverse everything and I just reflect my previous steps. That's it. I reverse my H, then I reverse my behavior at M. Great. But here something different happens. Why do I have this hysteresis loop? I'm doing exactly this. I'm starting from this point, right? I'm going down. I'm exactly at H equals 0. Okay, so H is equal to 0, and I'm having a positive magnetic moment. right? But if I'm starting from minus m0 and eventually I'm reaching a solution where h again equals 0, I'm having a negative magnetic moment. How come? Okay, so this is related to this peculiar behavior in the ferromagnetic state when I have two solutions. Okay, so I'm in ordered state. Why I'm in ordered? Because the magnetic moment, my magnetic or the total spin of the system is not zero. But it can have two states or two solutions. It can have either positive or negative. Okay. Yes.
גובה הנקודה האדומה זה בעצם תלוי בטמפרטורה?
Yep.
ככל שיותר קטנה זה יותר גבוה?
Exactly. So you see this height over here is exactly this height over there. Okay. And the lower part is this. Okay. So if we use a different T, the closer we are going to be to the critical temperature, the difference between those 2 points is going to converge to 0, and the slope is going to close. Okay? If we take a point that is far away from the critical temperature, those 2 points are going to be far away from each other. The larger the difference on the hysteresis will look for us. Now, yes?
Does it mean that when we decrease the temperature, we can make magnetic fields to appear?
Spontaneous symmetry breaking. Right? Pierre Curie was extremely fascinated by this, right? So you just change the temperature, you heat it up, or you cool it down, and then out of nowhere, a magnetic moment appears. Total magnetic moment, right? Now, and this is the question, what exactly happens here? And how to model it? Now, if you remember the last, and I will get to this, don't worry. In the last lecture, I have shown you that for the Bose condensation, this is exactly the plot we are getting, except this lower branch, right? So for Bose condensation, for high temperatures, there is a zero amount or zero proportion of the total particles that are sitting at the lowest state, right? As we cross this condensation temperature, the amount of particles that are sitting in the lowest energetic state is going up. So exactly the same happens here. So their transitions are somehow related. Okay? We will see exactly how and why. Okay. So can we explain all of this and this very interesting appearance of magnetic moment, self-magnetization, we can say it, out of nowhere when we cross a specific temperature, right? This critical or Curie temperature. And how exactly can we explain this irreversibility, right? We start from one point, we go to another, and etc., etc. If we assume that the particles inside this are not interacting, okay, none of this can appear. So if we somehow manage to take all those different particles with different spins and simply say, well, the spins are not interacting, let's try and find out what is going to happen. Then from such a perspective, it's impossible to get a spontaneous symmetry breaking. Because if the system, different spins are not interacting, okay, if the different spins are not interacting, it's impossible that, well, below some specific temperature, they suddenly will start to do something different and self-magnetization will appear. Okay? So it is an emergent behavior that appears only due to interactions of the spin. And what this plot tells us is that there are temperatures when we can neglect effectively the interaction between the different spins. It's not important so much. But there are regions in space, or in phase space, that are related to the temperature where the interaction is critical and it's important and we cannot simply neglect it. So this picture over here and this picture over there simply says to us that the prescription that we have, that everything can be separated in this not interacting particles, is simply wrong. Something very peculiar starts over here, and we will try to understand what exactly is going on.
מה עם דיאמגנטיות?
It's a different story. It's a different story. Diamagnetism is a different story. A little bit. It's related. All right. So in order to explain this, simple models were introduced. Now, the models were introduced 100 years ago. In the first one, I think, goes back to 1920. So it is Ising model. Okay. And the Ising model was proposed by William Lenz in 1920. He had a student, his name was Ernst Ising. This is why the name Ising model, that solved a one-dimensional version of this model erroneously in 1924. Okay, and then many people, so this is 1D in one dimension, and afterwards Lars Onsager found an extremely beautiful way to solve this problem in 2D. I will describe now. Nobody really knows how to solve this problem in 2D. Exactly solve this problem, this model in 2D with external field. Nobody really knows how to solve this problem in 3D. We'll try and see what are the differences between different dimensionalities and why this a difficult problem. Okay, so what is the Ising model? Let's assume that I have a lattice. Okay? So all this material that I'm describing, I'm just saying, well, I have a lattice, and this lattice can be one-dimensional, two-dimensional, three-dimensional. It doesn't really matter. Okay? But there are lattice points. At each lattice point, there is a spin. Okay. Sometimes the spin is points up, and sometimes the spin is points down. Okay. And the total number of lattice points where the spins are sitting is n. N number of lattice points. Now, William Lenz and Ising, they suggested the following thing. We need to describe, so let's treat everything in canonical ensemble. Okay, so the number of particles is not going to change, the number of lattice points is not going to change, right? And we're treating canonical ensemble. So in order to treat the canonical ensemble, we were going to say the following thing. We have the energy. It is minus h mu, okay, or mu 0, a sum over I Si. Okay, or let's call it SRI. Now, this is just the energy of those different spins if I have some specific external field H. Okay. Now we know, but we do know that something additional have to be included in order for this system to give the results that we are expecting. So there is some sort of a interaction energy that has to be included inside this model. And what exactly this interaction energy is? Well, the claim is as follows. The original claim of Lenz. So the different spins, somehow affect each other. How exactly they're going to affect each other? Well, we can couple them, and we can calculate the magnetic dipole, magnetic monopole. There are a lot of magnetic theories that actually say how those spins should interact. Now, they tried this, Lenz tried to simplify everything, and he suggested the following thing. So if we have two spins, S at position Ri and S at position Rj, the interaction has to be coming from the multiplication between the two spins. Okay. There should be some sort of multiplication between them. Okay. Now, of course, it's not a simple multiplication because we'd want one spin to interact with every other spin inside the system, but we do expect that if those spins are separated and the separation length is extremely large, so the contribution to the interaction energy should be small. Okay? So they included a coupling constant, which depends on the difference between Ri and Rj.
אנחנו פשוט נזניח מה שלא אחד ליד השני?
Why not?
הוא ממשקל את זה פשוט לפי המרחק.
So I'm just saying the following. So this guy affects that guy, right? I'm saying, but if they are, and this guy also affects this guy, right? So this spin interacts with this spin, and it also interacts with another spin over here. I'm saying the interaction energy is becoming smaller and less important as they are separated one from each other. Okay. Now, this interaction energy is between any two spins that we have inside the system. So we have to sum over all Ri, or all I's, and all J's. Right? So this is something that we have to include inside the system. Now, moreover, this interaction energy, should it be with a plus sign or with a minus sign? So let's include here a minus. Okay? Why a minus? So I do prefer from that if this spin is affecting this spin over here, they will try to be exactly the same direction. I don't care if this direction is up, down, sideways, I don't really care. So those two spins, the interaction, some interaction, tries to align the different spins together. Right? So this is why the minus. Again, I want to obtain as negative energy as possible, because the minimal, more minimal the energy is, the more preferred state it is. And I do want that this interaction somehow will affect the appearance of this spontaneous symmetry breaking, of this order. I do want that eventually that this interaction here will bring to me something that is related to appearance of the ordered state. Okay? So the idea is to couple every two spins inside the system. There is a coupling constant. This. Okay. And I sum over every two spins inside the system. Okay. Now, usually also there are sometimes it's multiplied by 1/2 over here, y 1/2, in order not to count all the interaction twice. Yes.
How do you treat your neighbors?
There is a specific value of this j when, so for example, this is R1 and this is R3. Okay, so the interaction between those two spins is SR1 dot SR2, R3, multiplied by j, the difference between R1 and R3. R3 minus R1. You will provide to me what the value of this function is. So I have a constant, a specific constant over here, multiplied by the value of the spin at position R1 and the spin at position R3. Okay. Provide me the different values of those coupling constants, and then we'll have an exact expression.
But you said that when they're far away from each other.
So what I expect that this R, if R3 to R1, or for example, I have R1, R3, and here is R100. I expect that this J let's call it R, which is the different distance between two spins, that it should go to 0 as R goes to infinity. Right? The farther away they are from each other, then the coupling constant goes to 0, and they less and less care about each other.
Only the closest.
Yeah, so the most important ones are your friends. Right? Friends and neighbors. You don't care about who is living like 200 kilometers up from here. So what is going to happen for this model and how exactly we are going to solve it? Okay. Great. First of all, it's really hard to solve this when we have SR1 or SR2. So let's see how first Ising tried to solve it in general setting when we have no interactions. Right? So I suggested that we do need interaction inside the system, right? So we do need this part. But who said that we actually need it? Maybe this part is enough. Maybe if you solve a system of non-interacting spins, we can obtain this transition from order to disorder. Okay? So let's try and see what happens if we have only this energy, we neglect the interaction energy, so it's free Ising. How we solve this part? Okay. So we have the following thing. We always start from the partition function. And the partition function is written as a summation over all states of all spins, right? E to the power minus h dot mu 0 sum over I si. Okay? Now, how to solve this? Okay, so we can basically say this is a sum over all states. I want to see what happens where we don't have interaction. All right? So first of all, I want to solve this problem without interactions. Then I want to show to you that it's actually very hard to solve with interaction. So we sum over all states over here. And what we have is I from 1 to n, e to the power, there is a beta over here, and there's a plus, right? Because, yeah, because it equals to e to the power minus beta e. So e to the power beta h mu 0 beta mu 0 SRI. Now all the different spins, I assume that since they are not interacting, what I mean by all states, I assume all states, all the different values of all the different spins. Okay? Now all those spins are now, when I have written this, and they are not affecting each other, and there is nothing in the energy term that somehow affects one behavior of one single spin, does not affect somehow the behavior of another spin. Okay, they are completely independent. So I have here a factorization n over all states of spin 1 e to the power beta mu 0 h dot s1. And everything is to the power n. Why? Because they are independent. This means that the system is factorizable. Okay, here it's going to depend what are exactly the different values of h and what are the different values of s1. So we can say the following thing, that s1 is having either +1 or -1 in the z direction. All right, and h also h in the z direction. Okay.
Why are you summing only over spin 1?
Does it important if I sum it over spin 2 or 3 or 4? All the different spins are not interacting. All the different spins are identical. So the transition here is that I managed to perform a factorization. Right? So this is the usual prescription. I have particles that are not interacting. Those particles are my spins. Right? They're independent from each other. And they're identical. So I can choose this one spin. I chose spin number 1. And I'm summing over all the different states of spin number 1. And then I take the nth power of this expression. Okay? So, great question. But let's assume, for simplicity, in those Ising spins, they obtain only +1 and -1. So it's a simplified model, right? It assumes that I have specific values of those S that can assume only +1 or -1. They cannot assume 0. Okay?
אנחנו מניחים שדה מגנטי קבוע.
Yep. H is constant.
זה מחייב במודל הזה?
No, but it becomes very... So if I assume that S can obtain different values, then H can obtain different directions, the summation here becomes more complicated. But the way how to solve it is exactly the same. Okay? So if we have these assumptions, what we obtain is that Z, okay, Z is a power n of what? E to the power beta h mu 0, right? Plus e to the power minus beta h mu 0. Okay? Which is 2 cosh hyperbolic cosinus of beta h mu 0. And all of this to the power n. Okay, so this is Z. Okay. Now, what is my order parameter? My own order parameter is m. Now, what m is equals to? A sum over I, SRI multiplied by mu 0. Average. Right? Because for each specific state, there can be different configurations. But we actually need to take the average value of this magnetic, of different realizations. Okay? Which is the average of a sum. It's a sum over averages. So it's mu 0, a sum I goes from 1 to n of SRI. Okay, so all the different spins are exactly identical, right? So the average values are also identical. So we can say that it is m equals to mu 0 multiplied by n S1 or SR1. Okay. Now we know what is the partition function of the whole system is. Okay, and now by using this function, we want to compute what is the average value of SR1. Okay. So what is SR1? It can obtain two values, either +1 or -1, right? So +1 in the direction z, okay? +1 in direction z, multiplied, what is the probability of the spin SR1 to point in the z direction? Exactly. So we're looking on, what is this guys here? It is z1 to the power n. Okay? So it is 1z probability to point in direction z minus 1z probability to point in direction minus z, which equals to, it is 1 direction z multiplied by this obtained from this guy over here, right? So it is e to the power beta h mu 0 divided by 2 hyperbolic cosine of beta h mu 0 minus 1 in direction z of e to the power minus beta h mu 0 divided by 2 hyperbolic cosine of beta h mu 0. Okay, so I've taken the expression of z1 over here, and I know what this is, the probability pointing upwards. This is the probability of pointing downwards, and I need to divide it by this cosine over here. Okay, so what we have over here, exactly. So z and z, it's outside, and we have e to the power beta h mu 0 minus e to the power minus beta h mu 0 divided by 2 cos beta h mu 0, all of this multiplied by z, equals to z multiplied, so this is what? No, but we can take the 2 over here. Okay? Beta mu h mu 0 h divided by a cos of beta mu 0 of h, and eventually we're getting the following expression for the magnetic moment of this system. So the magnetic moment of the system is what? Mu 0 multiplied by n, the total number of spins, hyperbolic tangents of beta mu 0 h, all right, multiplied by z. How this looks like as a function of temperature. So it's, this is m, this is t, okay? And so when h equals h, so it depends on h, you see? It depends on h. So if we take h equals to 0, right? H equals to 0. What happens here? What is the hyperbolic tangents of 0? 0. So for any temperature, it becomes independent of temperature. For any temperature, the magnetic moment, self-magnetic moment, is always 0. Right? It is something when h is not 0, right? It is something. As a function of h is going to be so if we plot m as a function of h, we're getting what we plotted beforehand for the paramagnetic state. Okay? This is as a function of h for any temperature. So this is paramagnet. And this is a paramagnet. It's only disordered. We need something, we need to change this model somehow. This is why we need this interaction energy, so that some additional solution somehow will appear miraculously over here, right? We need something that will start to go over there or over there. And we don't see it. We don't see it. So if we assume that all the different spins are not interacting in this Ising model, right? Then there is no description of what happens in nature. So we can say, well, it's a bad model, it's a bad description, or we can say, well, maybe something is missing. So physical modeling and any modeling is not to just to take and, well, bring everything inside. Let's take all the different magnetic interactions. Let's take all the different representations of the spins. No. The way physicists work is, I'm assuming the simplest possible explanation, and if it's not working, I'm adding up, little by little, additional ingredients. And in my case, those additional ingredients are going to be this interaction energy, right? Proposed by Lenz. I don't really know how to solve everything. I don't know how to treat this big, messy material with a lot of magnetic spins. But I do know how maybe to treat simple physical models and to see whether they can produce the expected behavior to the transition of ferromagnetic system, right? And if I can find such a model, maybe I can understand something about what's going inside. So let's try to see what happens if we do have some sort of interaction inside our system. So we do know how to solve non-interacting Ising model. And now we want to learn how to solve interacting models. So we have our box, we have different spins, and those different spins can point again. So this is H, Z. Our spins can point upwards or downwards, right? They are not exactly free. They are somehow interacting. And our energy is minus mu 0 H or Hz, the sum over I, SRI, okay, minus 1/2 sum over I, sum over J, JRI minus RJ, SI, SJ. And for all I, SI, either plus 1Z or minus 1Z. Okay. So this is our assumption. But there is interaction, and this is very important. Okay, so how we managed to solve this model when we don't have this interaction part? So what we managed to do, we looked on this and we say, well, this is just a sum. The moment that we have just a sum, okay, in the partition function, so we now want to go and say, well, Z is a sum over all states of e to the power beta E, right? And if this E only has a sum, so the sum is automatically becomes a multiplication. So it's a sum or exponent of a sum is a multiplication over exponents. And all those different multiplication terms are independent. But the moment that we have this coupling, Si and Sj, I cannot separate it into multiplicative terms where don't know how to separate into a sum over all states. And here I have multiplication of different functions that depend only on S1. So this is Fs1, and this is Fs2, and this is Fs3. I don't know how to do it, because if I can, or if I manage to perform this transformation from here to there, I can use factorization. But I don't know how to do it because I have this coupling over here. If I'll separate this sum, different values of Si are going to appear in different functions. So this is a hard problem. This is a really hard mathematical problem. This is why it has taken on Sager more than 10 years to solve this problem. But there is a method, and there is some sort of approximation. Yes? You can't.
Why?
Because you maybe can do this only in one dimension. But it's not working. It's not working because, well, it's different than the quantum problem that you're describing. Right? Okay. So what is the assumption? We're going to use something which is called mean field solution. What is a mean field solution? I look on the spins and I say, well, they are somehow interacting. The different spins are interacting, they're affecting each other. How they're affecting each other? Well, according to this part over here. Now, but eventually I can assume the following thing. I will say, well, I let the system sit, and all the different spins, they are flipping around. This spin affecting that spin, they are sometimes flicking around, changing their direction, right? But eventually I can say, all the different spins, let's take a different marker. All the different spins have an average value. What is this average value? M0. The average value for all the different spins, I will assume that eventually part of them are pointing somewhere. Maybe yes, maybe exactly the same direction, maybe no. So I'm assuming that there is an average value for all the different spins. And I'm assuming that this is exactly the same average value. Right? This is why it's called mean field. I'm basically saying, well, there is a mean approximation, mean value for all the different spins. And I'm going to assume that those different spins are not far away from their mean value. Right? So this is the assumption. I'm basically saying it is as if I have a specific preferred direction. I don't know what this preferred direction is. I will call it M0, the value of this direction. And I'm assuming that all the different spins, well, they can flip around, but they are not really far away from this mean direction M0. Okay. Now, let's see what is the mathematical approximation that I'm using, because I'm just saying to you, well, I can represent everything as if there is a mean, but there is always a mean. It's a stochastic variable, the direction of the spin. It can point either up or down, right? But I'm saying, well, there is a mean value of this of every spin. And what exactly the mathematical approximation when I'm saying the true behavior is not far away from the mean? Some sort, you will see. Okay. So I have, look on this guy over here. I have multiplications. I have SRI dot SRJ. Okay. This is what I have. This is the problem when I have a double summation. Now, let's write this down using these words that I just got out of my mouth. There is a mean value and the spin is not far away from this value. Okay, what it means that I want to write this guy as this M0. Okay, we can put a vector over it. And I'm writing this down as plus SRI minus M0 multiplied by M0 plus SRJ minus M0, the small m. Okay, so no harm has been done, right? I have done basically nothing. I will just open my parentheses over here, and I have M0 squared plus, not that they are different, right? Okay, so M0 dot SRI minus m0 plus m0 dot srj minus m0, and I also have plus sri minus m0 multiplied by srj minus m0. The mean field solution over here, when I assume, well, there is an average value and my deviations from this value are not big, is basically saying, let's get rid of this last term. Okay? This is what, in this perspective, mean field means. There is specific value, the fluctuations are not large, we're taking some of those fluctuations into account, but only the first order, and we neglect the second order of the fluctuations. Right? So now we have three terms, or let's open up this parenthesis over here. So we have m0 from here, we have minus m0 from here squared, and we have minus m0 squared from here. So we have minus m0 squared. Okay, here we have m0 dot sri, and here we have m0 dot srj. Okay, so this is sri dot srj. I neglected everything that involved maybe somehow the multiplication of SRI and SRJ. Right? So the moment I'm capable of doing this, maybe this technique, this old technique that we used so far so successfully in this class will work. Right? Because the problem was those terms, SRI, SRJ. Now there are no SRIs and SRJs, because I neglected something. Hopefully it will work, and see where it gets me. What do you mean why it's because I'm a physicist, I can do whatever I want, unless I'm in examination. Exactly. So this, think about the approximation. This, I'm saying this guy is small because the deviations from the average value is small. So this is the first order deviation. This is a second order deviation. So if this guy is small, this is extremely small.
How can you tell what's m0?
I don't know what's m0, right? So I have, this is a good question. I have no idea what m0 is, and hopefully eventually I will know something about it. But so far I don't know what m0 is.
But it's different m0 for each.
Great question. It's exactly the same. Okay. Why it's exactly the same? So what I'm looking for, I'm looking for, m0 is exactly the same for all the different spins, right? This is what I've written over here. This deviation is small and this deviation is small. So for any Ri and any Rj, this is exactly m0, the same m0. Why I'm saying that this is exactly the same m0? I'm looking for a specific solution. What is the solution? Total magnetization. So if all the different spins have exactly the same average m0, then there is order. And when this m0 is 0, it's disorder. So by plugging in this m0 everywhere, I'm basically hinting there should be a solution that is a transition from 0 to non-zero general value. It's like, it's cheating. Why? Not exactly, but why it's cheating? I know what kind of a solution I'm looking for. I'm looking for this transition, right? For this transition. I'm looking for such a transition for the general magnetic moment of the system. And I'm assuming that this will look like as if all the different ends or all the different spins have exactly the same average behavior. Right?
But if all the different spins have the same average behavior, then the whole system has the same.
Exactly.
But then if we find m0 that we...
If you find m0, so if you find m0 such that everything is satisfied, and we indeed find this behavior, then we are somehow correct. Okay? Any other questions? So we added m0 in order for that eventually what we're looking for. We're looking for the general magnetic moment of the system. And the general magnetic moment of the system M is what? Is a sum over SI mu M0, average. So it's a total magnetic moment, or the sum of different magnetic moments. Okay? So this is mu0, sum over I, SRI, average. And if I assume that here stands M0, right, and it's the same M0 for everybody, I'm getting that M equals to mu0 n multiplied by M0. If this M0 is 0, I'm getting paramagnetic behavior. If this M0 is non-zero, I'm getting ferromagnetic behavior. And hopefully, this M0 will eventually behave as expected.
אז הוא לא יכול להיות קבוע.
No, it's going to be a function of temperature. It's going to be a function of external magnetic field. It's going to be a function of all the different stuff that I have inside the system. Okay. We have now to obtain this sum, right? So we have 1/2 sum over I, sum over J, J R I minus R J, SRI, and dot SRJ. Right? Because all the different spins have to be considered. And 1/2 because I don't want to count them twice. Okay, so we are going to use this expression over here. We're going to use this expression over here. So we have 1/2 sum over I, sum over J, J Ri minus Rj, and what we have inside, minus M0 squared plus M0 dot SRI plus M0 dot SRJ. Okay, so basically we have 3 double summations over here. Let's treat the first double summation. It's 1/2 sum over I, sum over J, J Ri minus Rj, right? M0 squared minus. We can take this M0 out, right? So we have minus 1/2 M0 squared sum over I, sum over J, J Ri minus Rj, and then I'm saying the following thing. A summation over J of Ri minus Rj, I will call it J tilde. And I'm assuming that the sum is converging to a specific constant value. Okay? I can use it as R1. And I'm also saying that this J of R2 minus Rj also equals to exactly the same J tilde. And I'm assuming that a sum over J R3 minus Rj equals exactly to the same constant value J tilde. I'm basically saying the following thing. I'm looking, this is spin that is located at R1. Okay? And I'm going over all the different positions of all the different other spins inside my system. And I'm saying, well, I can compute, because it depends on the distances between the different spins. So here it's Rj. Okay? I can compute this guy. Let's assume that I can perform this sum, right? And this sum equals to J tilde. Now I'm saying, well, but does it matter if my system is extremely large and is very, 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 very big? Does it matter if I start from R1 or if I start from here, from R2? because I'm summing over all the different positions of the other spins. Okay, so this sum is independent if I put here R1 or R2 or R3. Okay, so it is called, the system is translationally invariant. It doesn't matter from which point I start to count. Right?
But Stas, the distance is much farther.
Yeah. But it's converging. It's like an integral. Let's assume that I have an integral. Okay? So what I'm saying to you is the following, that I have this summation. Okay? I sum over all the different systems, over different positions of the spins. So this sum I'm simply saying, well, this is a summation over J, and here it's an R. What is R? R equals the difference R1 minus Rj. You know that when this distance goes to infinity, or it's very, very large, J goes to 0. So my assumption that this guy is indeed converging to J tilde. So I cannot use just any function. I have to use a function such that this summation will converge to a finite value. This is very important. Okay. So if I have this translational invariance, let's look on this sum over here. So the first sum is minus 1/2 m0 squared sum over I sum over, and the sum over j, what I know, that this is j tilde. Okay. So this is the total number of the particles that I have inside my system. Exactly. So this equals minus 1/2 m0 j tilde n, and m squared over here. So this is the first part. We managed to single out this sum. Okay. Now we have the second part. What is the second sum? So it is 1/2 sum over I sum over j. Okay, and we have m0 dot sri, right? I'm sorry, there is a j over here. J ri minus rj m0 dot sri. Okay, this is the second sum. I can sum over I and then I can sum over j, so let's put it as 1/2. Okay, we can put m0 over here, dot, a sum over I, sri vector, dot, without a dot, a sum over j, j, ri minus rj. But this, I know what this sum is. Right? This is the sum over here. It's irrespective of R1, R2, or 3. I only need to count over all the different RJs. So it equals to 1/2 m0 dot a sum over I sri vector. This is the second sum. There is a third sum, right? What is the third sum? So we did that. We did this.
Where's the j tilde?
Where is the j tilde? Oh, it's important. J tilde is over here. That's okay. What is the third sum? So it is 1/2 sum over I, sum over j, j ri minus rj, multiplied by M0 Srj. Okay. So first of all, let's flip the order of summation and take M0 out. So we have 1/2 M0 a sum over j, Srj, a sum over I, j, Ri minus Rj, which equals to 1/2 M0 vector dot a sum over j, Srj, dot a sum over I, right? A sum over I, j, Rj minus Ri. And this equals exactly to j tilde. So it is 1/2 M0 vector multiplied by sum over j, Srj, and here is a j tilde. Okay, so we have three terms. This guy, don't worry, it will be over soon. This guy, and the other guy.
Can't we say that those terms are...
Those terms are exactly the same because you don't care if I sum over I or I sum over j, right? It's a dummy variable.
זה ברור שזה יהיה גם האחרון. זה בסך הכל אינדקס.
Yep. So,
לא, זה לא שורר בהתרשמים פשוט. קל לראות.
the interaction energy we're getting, it is what? It is j tilde M0 dot a sum over I Sri minus what we have there, 1/2 M0 squared j tilde n. And the total energy is, what was the total energy? Minus h, or we have mu0 here, dot a sum over I Sri minus j tilde n0 dot Sri sum over I Sri plus 1/2 M0 squared j tilde n. This is our energy. Let's write down the fun part, the partition function. Why is it the fun part?
Because it's finally over.
No, because it's we already know how to solve it. We already know how to solve it. Okay, so z equals sum over all states of e to the power minus beta e. It equals to sum over all states of what? E to the power minus, and we write down all these terms inside, minus beta, and inside we have minus mu0 h dot a sum over I Sri vector vector minus j tilde m0 vector dot over a sum over I Sri, and we also have plus 1/2 m0 squared j tilde n. Okay. It is a sum over all states, exactly, e to the power minus beta m0 squared j tilde n divided by 2. Okay. So we multiplied by e to the power of beta, and here we have mu0 h plus j tilde m0 vector dot a sum over I SRI. This equals to, we take this out of the summation, e to the power minus beta m0 squared j tilde n divided by 2. Here we have a sum over all states e to the power beta mu 0 h plus j m0 dot sum over I SRI. But this is easy. Why it's easy? It's trivial. Why it's easy and trivial? Exactly, we will know how to solve it. Let's call all of this
Trivial.
trivial. That's trivial. That's trivial. Don't write it in the exam. It pisses me off. Okay. So this is, we can call it as some sort of a mu 0 h effective. Right? We can call it like this.
רגע, סטאס, יש לי שאלה.
כן.
איך עשינו את ה-J טילדה החוצה? הוא לא תלוי במצב.
No, J tilde was just a sum. A sum over all the
הוא
different.
קבוע לגמרי?
Yes, it's an J tilde was independent. It's a sum over J R I minus R J, and I'm claiming that it's independent of R I because the system is translationally invariant. We can in exam you will be capable of solving this. Don't worry. No. Look. I have to provide to you a specific J, right? And I will provide to you such a J that you are capable of doing this summation. And usually this J is very simple. It only counts nearest neighbors and that's it. So it's affecting the guy over here, it's affecting the guy over there, and it's zero everywhere else. So it's not an infinite summation. Usually it's a finite summation. And you can do it. Don't worry. You will see how to do it. The TAs will show it to you. Don't worry. Right. This is an effective external potential, external field, right? I can call this, right? I can basically say that this is mu 0 multiplied by h plus j tilde divided by mu 0 multiplied by m 0, and all of this is h effective.
M has the same units as it's a magnetic field.
Yes. So j multiplied by m is the same units as mu 0 multiplied by h. Okay. The moment that we know this, we already have shown to what is the solution of this guy. It's just the hyperbolic cosine. So z equals to, we have this first part, which is different, e to the power minus beta m0 squared j tilde n divided by 2, and here we have 2 cosine of what? Of mu beta mu 0 h effective, right? To the power n. Okay. Let's write it explicitly. So it is e to the power minus beta m0 squared j tilde n divided by 2, and here we have 2 hyperbolic cosine beta mu 0 h. Remember, h vector is h multiplied by z. All right. Plus what we have over there, j tilde, it's a scalar. Mu 0, it's a scalar, and here we have m0. Right? And all of this to the power of n. So we managed. Sorry? M0 was vector. This is trivial, right? We already done it once. We already done it once, and the h was also a vector, and it's eventually appeared to h value. You go backwards and you say how we managed to solve the non-interacting Ising. Here I have a non-interacting Ising, and I have a different field. That's it. Right? So it's already too late. but the technical and the difficult part is over. Right? We have the partition function. Right? Now we have a question. Does this partition function actually lead to the behavior that we are expecting? What is the behavior that we're expecting? That the total magnetic moment of the system is going to be, as a function of temperature, is going to perform this type of behavior. Okay? Now, we don't really know, and we cannot see it from here. Why? Because, well, previously, we simply would set h to 0, and that's it. Now we have something else inside our equation. We have an unknown. What is this m0? Right? I assume that there is m0, but what is this m0? So we have z that is somehow dependent on a parameter that I have no idea what this parameter is. Right? So we indeed have solved the technical part. And this is the solution due to min-field. But we have not finished it. Why? Because we need to think about a way how to define m0. We need a self-consistent equation to find m0. And how exactly to do it, we will see on Tuesday. מה? לא, אתה צריך להסתכל על טמפרטורה יותר, יש לך TC, ממש, היא לא 0.
כי m0 יש ב-T שווה 0, m שווה m0.
כן, אתה תראה אותי, כן. אבל לא צריך את זה, אני אראה לך איך עושים את זה. כן. כבר לא, תסתכל איך עשינו את זה עבור האייזינג החופשי. גם שם, זה בדיוק אותו מעבר כמו שם, לכן רציתי לחסוך את הזמן הזה. הם כבר לא וקטורים.
יש שתי שאלות.
כן.